Hi, this is Mark Maclaine. This is a video on rounding, estimation, limits of accuracy, upper and lower bounds, and percentage error. Okay, so if we're going to be rounding, there are three types of rounding that can happen. The first is if we're asked to round to the nearest 10, 100, 1,000, also tenth or hundredth, etc. So this, say for example, we have a number 38,526. Now my 5 is absolutely terrible here, so I'm just going to make sure that's a bit better. Now, if we're asked to round to the nearest 10,000, this is what happens. So here we have our 38526. Now this is our units here, because there would be a decimal place here. These are the tenths, these are the hundredths, these are the thousandths, and these are the 10,000ths here. Okay, now if I'm asked to round to the nearest 10,000th, this is my 10,000 digit here, which is the 30,000 in the 10,000 column. Now what we do, if we're rounding to the nearest 10,000, what we do is we look at the number after that, okay, the number just after it. All the other numbers aren't relevant. They don't matter. So all those ones don't matter. It's the number just after it that matters. So what we have here is we have an 8. Now, if the number is 5 and above, it causes this first number to round up. If it's 4 and below, then it stays the same. But because this digit here is 8, you have this 8 here, it will cause that to round up. So our digits will become 40000. So what that done is that 8 has caused the 10,000 to round up to the nearest 40,000. Okay, so that is to the nearest 10,000. But say, for example, we had the same digit, 38526, and we're asked to round it to the nearest 1,000. So we have our 38526. Now, again, here is our units, tens, hundreds. These are our thousands there. So I'm being asked to round it to the nearest 1,000. Now, the digit before that, the 3, is still the same. But we look at the digit after this, which is a 5. So the one just after the 1,000, and that will tell us whether it rounds up. Now in this case, because it's 5 or above, it is 5, it'll cause our 8 to actually round up to a 9. Okay? And then we place zeros after that. So the answer is 39,000, and that's to the nearest 1,000. Again, if we're doing it to the, say, 38526, and we're asked to do that to the nearest 100, okay, so this was to the nearest 1,000, and this will be to the nearest 100, okay, what we do is we got our 38526, and create my columns here. This is units, tens, hundreds, thousands, 10,000s. Now what we're doing here is I'm rounding to the nearest 100 in this case. So my digits before that are unchanged, 38. Now we look at the digit just after that 100, which is the 2. Now because this is 5, it's below 5, it makes it round down or essentially stay the same. So that 5 doesn't change, and that is that. Okay, so this one here was to the nearest 10,000, this was to the nearest 1,000, this was to the nearest 100. Now, the next type of rounding happens where you've got essentially where you're asked to round to decimal places. So say, for example, I've got pi, 3.1415, ... Okay, now if I'm asked to round this to 3 decimal places, what we do is I take the number, so this is my representation of pi, we write it 3.14159, okay, and we take the 3 decimal places. This is the first decimal place, this is the second, this is the third. Now decimal places are numbers after this point, after the decimal point here. Okay, so we take the 3 digits after the decimal point, which is the 141, and then what we do here is we look at the digit after those to see whether it's going to round up or down. Now this 9 and other digits after that don't matter, they're not relevant, it's just the digit right after that. So in this case we can see the 5 will cause this 1 to round up. So the other digits are unchanged, so 3.14, but the 5 caused it to round up to 2. So it is 3.142 to 3 decimal places. Now, if we were asked to do it to 2 decimal places, okay, so we have our 3.14159, okay, what I'm going to do is take 2 decimal places here, and I draw a line here after that, and I look at the digit just after it. Now again, these ones are irrelevant, they don't matter, it's just the digit after those 2 decimal places. So before that, the 3.1 is unchanged. Now we can see, because this is a 1 here, it rounds down, it basically is below 5. So this keeps it as 4. So that is 3.14 to 2 decimal places. And then if we're going to do it to 1 decimal place here, 3.14159. Okay, and what we're going to do is just 1 decimal place here, we can see. So I draw a line just after that, and it's the digit just after that that causes it to either round up or down. Now, because that's 4, it causes it to round down, as in to stay the same. So it becomes 3.1 to 1 decimal place there. Okay, so remember, anything that's 5 and above will round the number up, otherwise it stays the same. Okay, so that's now the third type of rounding is to, so these ones are to decimal places. And the third type is to significant figures. So, okay, terrible writing there. To significant figures. Now what I'll do is I'll do pi again, 3.14159. Okay, now significant figures are the first numbers that aren't 0 as you move from the left. Okay, now it is possible that there would be a 0 in the hundreds column and a 0 in the tens column, but we don't write those. So we don't actually have to have them in there. But what you do is you move from the left and you count how many, essentially you count every non-zero digit. So the first number that's not 0, so this one here is a 3, and this one here is a 1 and a 4. So if we're doing this to 3 significant figures, 3 SF, what we do is we move along and we've got our pi. So we do 3.14, and what we do then is we draw a line here, and it's the digit just after that. Remember, all other digits don't matter. It's the number just after our third significant figure. And so that would be 3.14. And because this 1 here is below 5, essentially it's just a 1, it keeps that the same. So it's 3.14 to 3 significant figures. Of course, if we were going to do to 4 significant figures, 3.14159, here what we do is we go 1, 2, 3, 4. Okay, I draw a line here. That 5, remember all the others don't matter, the 5 causes this to round up, which gives us 3.142 to 4 significant figures. Now remember, the decimal places will tell us how many decimal numbers there are. The significant figures will count all digits that are before the decimal place as well. So for example, if I have this number, 38526, if I'm asked to round this, so let me just draw a line here. If I'm asked to round this here, so asked to round it to say 3 significant figures, which actually, by the way, is something that's very common for GCSE. What we do is, and in fact you should generally be rounding to 3 significant figures anyway, unless stated otherwise. 1, 2, 3, and then I draw my line here, and you can see the 2 means that the 5 stays the same. But if this 2 here was larger than a 5, if it was 5 and above, it would cause the 5 to round up to a 6. But here it is, it's 38500. And so that is it to 3 significant figures. Now, the important thing to remember is these 2 zeros here are known as placeholders. If you don't put those 2 zeros after that, then this would be just 385. But it's still 38,526. Rounded is 38,500. So that 26 is rounded down. So this is the same as rounding to the nearest 100 in this case. Now, I talked about this non-zero thing. So it moves from this, move from the left, and it's the first digits that are not 0. So let me explain that. So say, for example, we've got 3, 300,520, and we're being asked to round this. Okay, so that's 300,520, and we're asked to round to 3 significant figures again. Here we go. So what we do is we write out 300,520, and we count our significant figures. Now the 3 is the first significant figure, but it's also the next significant figure is this 0 here. The 0 becomes significant as soon as you have a digit that is significant. So this 3 means that all digits after it now become significant. All the ones before it, all the zeros that are there, are not counted. Okay, so essentially that's 300, and that's it. Those are our 3 significant figures. We look at the digit after that, which is a 5. This causes the 0 to round up to a 1. Okay, so the answer will be 301 and then 000 here. So 301,000 to 3 significant figures here. Okay, we need these 3 digits after that as placeholders to make sure it stays as 301,000, not just 301. Okay, now how does that work for decimal numbers? We'll have a look at this. So 0.00586, and say, for example, we want to round to 2 significant figures here. Okay, so we're going to round this to 2 significant figures. What I do is I got 0.00586. Now we move from the left. All of these are zeros, so they're not significant until we hit the 5. Now everything after that becomes significant, and we're just doing 2 significant figures. And that, I draw my line here. This 6 here causes the 8 to round up to a 9, and the answer is 0.0059. And what we have is we have our 2 significant figures here, and the digit after that, which was this 6, caused the 8 to round up to the 9. Now, sometimes these can be quite difficult when we have numbers like this. So say, for example, we've got 0.998, for example, and we want to, here we go. I want to make sure my writing is legible here. So there we go. Let me just go to here. So we're going to round to 2 significant figures here. So what happens is 2 significant figures, we're going to move from the left, and this is our first significant figure, this is our second here, and we have an 8 after it. Now, because the 8 is 5 and above, if it was 5 or any number above, it is, it causes the 9 to round up. But what's going to happen here is when the 8 causes the 9 to round up, the next number above 9 is 10. Now, 10 can't be written as a digit within here. You can't write a 10 in there. What actually happens is it carries a 1 over to this 9 here. So, in practical terms, what does that actually mean? Well, what ends up happening is we have 0. Now, this 8 makes the 9 round up, okay? So, this is 9. It causes this 9 here to round up to a 10, which then adds 1 to this 9 here. But the problem is this 9 here, when it gets... we've got our zeros here, but because it's just to 2 significant figures, okay, this will be your first significant figure, and that will be your second one. So we don't need these 2 after that. So that is 2 significant figures. So that's a slightly tricky question because you need to make sure, but you need to. Now, many of you will be aware that this 0 after here is not required because 1.0 is the same as 1. However, we do have to write this 0 here to make sure that we know it has been rounded to 2 significant figures. So, as a recap, we've looked at the different kinds of roundings. So we've got rounding where you're doing it to the nearest 1,000 or 100. Now, the other thing you can do with these is sometimes you can round to certain decimal places. So what you can do is, say, for example, we've got 0.386, and we're going to round to the nearest 1/10. Okay? So in this case, we've got 0.386. These are our units, these are our tenths, these are our hundredths, and these are our thousandths, essentially. So those are the columns. Now, what we're going to do is round to the nearest tenth, which again is this one here. Okay, and that's then we look at the digit straight after that, which is the 8. It'll cause it to round up, so that is 0.4. Okay, and that is to the nearest tenth. Okay, so that is where we're rounding to the nearest tenth. Now the next one was rounding to decimal places. So all you do is you write the 3 decimal places, just underline the 3 decimal places, and significant figures, you start from the left and you move right, counting your significant figures once you've hit a digit that is not 0. Okay, and where that actually applies most is in these decimal questions here, where you move right, and then these are our 2 significant figures here. Okay. The next thing to cover is estimation. Okay, now, in order to estimate something in GCSE maths, what we actually do is we will be rounding, we round to 1 significant figure. Okay, so we're going to round to 1 significant figure. So this is how you estimate mathematically. So say, for example, we've got a question of 23.8 times by 0.4, let's say 482 divided by, say, 11.6. Now, for each of these terms essentially within here, so the 23.8, the 0.482 and the 11.6, you just round each of those to 1 significant figure. So 23.8 would round to just 20. The reason for that is because 23.8, 1 significant figure, the first significant figure is the 2. We look at the 3 after it, which doesn't cause it to round up, so that is 20, and we only have to put the placeholder 0 there. Okay, the next one is 0.482, so the first significant figure is that 4. We then look at the digit after that, which is the 8. It causes it to round up, so that would be 0.5. Okay, and then at the bottom, on the denominator here, 11.6, the first significant figure is the 1, meaning that the second significant figure is this 1 here, but it means that causes the 1 to just stay the same, so that is over 10 here. So we know that 20 times a half is just 10 over 10, and the answer here is 1 as an estimation. So whenever you're estimating, just make sure that you round everything just to 1 significant figure. In GCSE Maths, you'll often be asked to find upper and lower bounds. Okay. Now, what are they? Well, whenever a number has been rounded, the problem is we don't know exactly what it was rounded to. So say, for example, I had this number, 0.35. Okay, now the problem with 0.35 is, well, not problem, sorry, if 0.35 gets rounded to 1 decimal place, so say, for example, it's rounded to 1 decimal place, what that will mean is I look for my 1 decimal place here, and the number after it was a 5, so that will cause the 3 to round up to 0.4, okay, as 1 decimal place. Now, if I told you that a number is 0.4 to 1 decimal place, the problem we've got is we don't know what it was rounded from. Now, of course, we know that it was rounded from 0.35, but if you were just given the information that it was rounded from 0.4, we don't know whether it was rounded from 0.35, but also the 0.41 would have rounded to that, 0.42 would have rounded to that, 0.43, etc. Also, 0.39 would have done that. 0.38 would have rounded. So what we can do is we can create what's known as upper and lower bounds for this. So let's have a look at this. So if we have 0.4, which is the number that's been rounded to, it could also be 0.41, 0.42, 0.43, 0.44, and 0.45, I hope you can see, would have rounded up to 0.5. So we don't, so essentially, that's the sort of that's the upper limit, basically. Okay. Now, in terms of lower limits, 0.39, 0.38, 0.37, 0.36, 0.35, and then 0.34 would round down to 0.3, so not to 0.4, which is our number here. Now, what we can say here is that 0.35 is known as the lower bound. Okay, this is the lowest value that would have rounded up to 0.4. Okay, so lower bound. The upper bound is a little bit more complicated. The problem is we can see that 0.44, because of the fact that the first digit here, because if it's to one decimal place, would round down to 0.4. But so would 0.441 or 0.449 or 0.449999 ... Now the problem is that until you get to 0.45 here, okay, so until you get to the 0.45, we can keep going 44999 ... forever, essentially. Now, the difference, if a number has a difference of 0, you could say that if two numbers have a difference of 0, you could say that those numbers are the same thing. And what actually happens is this 0.449999, as we carry on going, actually tends to become 0.45. It will eventually be the same as 0.45 once you have an infinite number of 9s. Now, instead of writing all these 9s out, it is acceptable to say that this is your upper bound, the 0.45. Of course, we know that 0.45 would round up to 0.5, but it's the upper bound. It's kind of your ceiling to your number. So we can, instead of writing the 0.499999 going on forever here, we can actually, it's acceptable to say 0.45, okay, as your upper bound. Now, of course, if x was your number, here, if x was your number of 0.4, we could say that x would be between 0.35 and 0.45 here, that would round to the 0.4. Okay, but what we do is we say that x is greater than or equal to 0.35 because it will include 0.35, but we can see that rounds upwards. But it is just smaller than 0.45. It doesn't actually include the 0.45. But for calculations, we can use 0.45 because our answer, when rounded to the three significant figures, would essentially be the same thing. So let me show you another example that hopefully make it a little bit clearer. Say, for example, I've got 3.6, and that is to two significant figures. Okay, so what I'm going to do is try and find the upper and lower bounds for 3.6 to two significant figures. So what I do is I say, well, 3.6 here. Now, what is the next two significant figure number above that is what I ask myself. So I know that 3.7 would be the next number that is to two significant figures above 3.6. And what would the next number to two significant figures be below that? It's 3.5. So this is our 3.6 here. Now 3.7 is not the same as 3.6 and 3.5 is not the same. Okay, but what I do is I go halfway between the two of those, which should be 3.65. That's my upper bound. And halfway between the two of those, which is 3.55, and that is my lower bound here. So in order to, one of the easiest ways to find your upper and lower bound is find the number that's above it, the next number above it, and find the next one below, and halfway between the two of those will be your upper and lower bounds. Because of course, everything in this section here would have rounded down to 3.6, and everything in this section would have rounded up to 3.6. So these are the values. Now this is the upper limit, remember, so it doesn't actually, 3.65 of course would actually round up to 3.7, but that's our upper ceiling number, and then 3.55 is the lowest possible number that would still round up to 3.6. If we're going to use a whole number, which could happen, say, for example, someone someone throws a ball 22 meters to the nearest meter. Okay, so someone throws a ball 22 meters to the nearest meter. Okay, well, what then, if I want to find my upper and lower bound, what I do is I say, well, what's my next meter above it? Well, that'd be 23 meters, okay? And what's my next meter below that would be 21 meters. So again, what I do is I find my midpoints to this. Okay, so my midpoint for this would be 22.5 meters. That would be my upper bound. And halfway between 21 and 22 is 21.5 meters. And that there is my lower bound. Okay, so essentially that's how we can find them. Now, these can be used in a variety of different ways, but essentially they're just mostly used in GCSE maths just to allow us to find an upper and lower bound, the possible, essentially the possible maximum distance that could have been thrown and the possible minimum. Now, in fact, what can happen sometimes with some questions is, say, for example, someone ran 100 meters, okay, to the nearest meter, and they did it in 10 seconds. Okay, to the nearest second. Okay, to the nearest second. Now, what they can ask sometimes is, what would the maximum speed be? Okay, so what would the maximum speed be that this person could have run? Okay, we're looking at Usain Bolt kind of speeds here. So this is it. So if you have 100 meters to the nearest meter, and they ran that in 10 seconds to the nearest second, what's the maximum speed? Well, first of all, we know that speed is distance divided by time. Okay, so that's the equation for it. So in order to get the maximum speed, now hopefully you can see this, to get the maximum possible speed in this, now, very often they'll say, what is the upper bound for the speed? And that gives you a clue that you're going to be doing upper and lower bounds for this question. What we're going to do, in order to get the maximum speed, you want someone to run the maximum possible distance in the minimum possible time. Okay, now hopefully that makes sense to you. You want to go really, really far in a very short amount of time, and that will give you your maximum speed there. Okay. So what are you talking about, Mark? You know, maximum distance in a minimum time. Surely this person ran, you know, the distance they ran, and they ran in the time that they did. Well, actually, what we're told here is that it's 100 meters to the nearest meter, and it's 10 seconds to the nearest second. So what we can do is find, for the 100 meters here, we can find our upper and lower bounds. So look, here's 100 meters to the nearest meter. Now, what's the next meter above 100 meters? It's 101 meters. And the next meter below this is 99. So again, we find our midpoint here, which is 100.5 meters. Okay, and that's my upper bound. And the lower bound will be 99.5 meters. And that will be my lower bound. Okay, so the problem is, because this person ran 100 meters to the nearest meter, we don't know they definitely ran 100 meters. They might have actually ran 100.5 meter, 100.5 meters, or they might have run 99.5 meters because it hasn't been measured. Now, of course, it's likely that it's probably be close to 100, but you know what? If it says to the nearest meter, it could have been as low as 99.5 meters. Now, again, because we're trying to do the maximum distance, I'm going to say, right, the maximum possible speed will be given with a maximum distance if this person ran 100.5 meters. Now, let's look at our time. We've got our 10 seconds. And that's to the nearest second. Well, 11 seconds is the next second above that, and 9 seconds is the next one below that. Well, do our midpoints here, which is 10.5 seconds. And we've got 9.5 seconds here is the quickest that this person could have run it in. Okay, now again, we're trying to find our minimum time, so I'm going to use my lower bound for the time. Okay, and that's the upper bound there. I'm going to use the lower bound for the time. So what we can then do is we can say, all right, well, so to get the maximum speed, okay, to get the maximum speed, what we're going to do is we're going to do the maximum distance, which was 100.5 meters, and we're going to divide that by the minimum time, okay, which was 9.5 seconds. So that is 100.5, and I'll do that in my calculator, divided by 9.5, and that gives us a speed of 10.5789 meters per second. So we're going to do that to three significant figures. That'll be 10.6 meters per second. So that's 10.6 meters per second with the maximum speed. But look, if we wanted to know what the minimum speed was that they did it in, okay, we actually use our minimum distance, okay, which was 99.5 meters, and we divide it by the longer time, okay, the much longer time. And what we've got there is 99.5, okay, divided by 10.5, which actually is 9.476, which is, now I'm going to do three significant figures, 9.48 meters per second. So you can actually see that there is quite a dramatic difference between our maximum speed and our minimum speed, just because there were errors within the working out, well, actually the measuring of the time and the distance. Now I'm just going to do a little talk about percentage error here, just very quickly. Whenever there's percentage anything, so for example, percentage profit, or there's percentage gain, or percentage loss, or percentage error, what we do is the equation is, in this case, profit over the original times by 100. That's your equation, essentially. For percentage gain, it will be your gain over your original times by 100. For loss, it'll be how much you lost, there we go, over your original times by 100. And the important one here is percentage error will be your error amount over your original amount times by 100. There we go, it's terribly written. Okay, so that is your percentage error there. It'll be your error over your original times by 100. Now, how do we apply this? Well, say, for example, you're asked to estimate a value, okay? So, for example, you're asked to estimate 120 times by 3.6 over 4.2, something like this. So what we do is we round each one of these to one significant figure, so that would be 100 times by, and then 3.6 would just be 4 over 4 here, okay, because that's 4.2 would be just 4. So in this case, what you've got is 400 divided by 4, which of course will just be 100. So that's our estimated value, okay, so that's fine. But if I actually then work out what the actual thing is in the calculator, so if I say 120 times by 3.6 is 432 divided by 4.2, and I divide that by 4.2, that actually gives me 102.857. Now, to work out my percentage error, what I do is I work out what my error is, how far off I was, out of the original amount, the correct amount here. So this is the correct amount. So essentially what I've got here is my error will be 2.857 out of my actual original amount, which is 102.857 here, and then what I'll do is I'll just times that by 100, and that will give me my percentage error. So here we go, and I'll do that divided by the 102.857, and that tells me, times that by 100, that tells me that I'm roughly 2.77% error, essentially. But that's what my that's how far off I was, essentially. This doesn't come up a huge amount, but it's useful to understand how it works and how to apply any of those equations. Now, finally, one question that does come up quite often in GCSE maths is to express a value to an appropriate degree of accuracy. Now, say, for example, we had an upper bound of 35.235, and we had a lower bound of 34.826. Now, to express this value to an appropriate degree of accuracy means essentially that both the upper bound and lower bound will round to the same number. Now that means that we have to try different significant figures to see which ones round to the same value. So now, say for example, we round this to 4 significant figures. Okay, so 4 significant figures here. The upper bound would be, so 1, 2, 3, 4. Okay, what would happen there is the 5 would then round the 3 up, so that would be 35.24. Okay, now our lower bound in this case would be, so we have 1, 2, 3, 4, and the 6 would round the 2 up, so that would be 34.83. Now, the question we have to ask ourselves is, are those two the same value? And the answer is no, they're not the same value. So now what we then do is we do to 3 significant figures. Okay, so the upper bound and the lower bound here, we can test those values. So to 3 significant figures would have been 1, 2, 3 here. Okay, in which case that 3 would then round up, keep the 2 the same, so that'd be 35.2, and the bottom one here would have been 34.8. And the question is, are they the same? The answer is no, they're not. So now, once we've done that, we try 2 significant figures, and here's our upper bound and our lower bound. There we go. So that would be 35.2, which would be just 35, and 34.8 would round up to 35. So in this case, we can say that whatever the question was here, if we were asked to express these values, so if we had an upper and lower bound, if we were asked to express them to an appropriate degree of accuracy, we know that the answer will be 35 to 2 significant figures. So we can see that our upper and lower bounds will both round to 35 if they're to 2 significant figures. There we go.